Hi, everybody. My name is Martinez de Velasco, and I'll be talking about Ramsey-comb spectroscopy of the X2EF Q0 transition in H2 and D2. And these are measurements that we completed over the last 6 months or so at our lab in Amsterdam. And I'm in the group, I'm a PhD student in the group of Kjeldijken. So we've heard a bit about this already, and also we've seen a plot that depicts the same thing. But the reason that we're interested in the X2EF transition is that we can use it to then, together with the group of Professor Merck in Zurich, to determine the ionization energy of molecular hydrogen. And that turns out to be one of the key ingredients to determine the dissociation energy. And the dissociation energy is something that can be calculated very precisely and that we can then use as a benchmark for tests of theory. And so we see here the plot that was shown this morning, where we have the uncertainty in the dissociation energy on the y-axis and the year on the x-axis. And we have here the Langmuir experiment that started off the day. And so we can see indeed that as experimental uncertainties go down, they push for theoretical progress, which then pushes for experimental progress and so on, until we get to the current status, which is that the dissociation energy of ortho H2 was determined with 340 kilohertz uncertainty. And for para H2, so with nuclear spin equals to 0, with 929 kilohertz uncertainty. And the theory uncertainty for both is about 780 kilohertz. And as was shown this morning, we're approaching the level at which the uncertainty in D0 would allow for the determination of the proton charge radius with an uncertainty that's smaller than the discrepancy that started the proton charge radius. Yes. So here is the thermodynamic, so-called thermodynamic cycle that was introduced earlier this morning. So we don't measure the dissociation energy directly, but rather we determine it by combining the ionization energy of molecular hydrogen, which is here in green, the dissociation energy of the molecular hydrogen ion, which is here in black, and we subtract off the ionization energy of atomic hydrogen here in purple. And you can see that the uncertainty for these terms increases as you increase the number of bodies in the problem, from 3 kilohertz with atomic hydrogen to 18 kilohertz in the 3-body system of molecular hydrogen ion to 940 kilohertz for the ionization energy of H2. And so we focus on the ionization energy of H2. And like we heard this morning, there are 2 ways that we do this, combining our efforts from Amsterdam and Zurich. One is to measure from the X to the GK state, which is what the group of Wim Ubachs did. And in Kjeld's lab, we work on the determination of the interval from the X to the EF state. Now, the measurement from the X to the GK state was done in 2018, or published in 2018, and it allowed for the determination of the dissociation energy with 749 kilohertz uncertainty. However, this experiment, this measurement, was limited by the AC Stark shift, residual Doppler shifts, and a residual frequency shift. And I didn't mention that, so we go to the EF or GK, and from there, the group of Professor Meck does transitions to high-end Rydberg states and then extrapolates using multi-channel quantum defect theory. So also in 2018, we then took a different route in Kjeld's lab, and we measured from the X to the EF state, the Q1 transition at 201.8 nanometers, and we could determine that with 73 kilohertz accuracy. And so this 2-photon transition in ortho H2 allowed for the determination of ortho D2 with 340 kilohertz accuracy, uncertainty, like I said earlier. And this number was in remarkable agreement with theory. However, our measurement from back then, from the X2EF, in, again, I have to stress ortho H2, was limited by the line width of our laser, by Doppler broadening, transit time broadening, and by the unresolved hyperfine structure of the ground state. And notably, if we go to para H2 with nuclear spin equals to 0, we don't have this problem. And so that's what we chose to do for the last measurement campaigns. So we did the measurement of now the rotationless Q0 transition, also around 202 nanometers, to the EF state. And before I talk about how we do it, I have to say a few words about frequency combs because we use them in a different way than most groups that do direct frequency comb spectroscopy. So frequency combs are lasers that can output a train of very short pulses where the timing separation between the pulses is determined by the round trip time of the light in the laser cavity and is very well controlled. So we can control the delay, the repetition frequency between pulses by changing the cavity length of our laser. And importantly, the phase slip from frequency comb pulse to frequency comb pulse is also very well defined. So we can also keep track of that very well. And here you have the typical frequency comb spectrum, where typically for direct frequency comb spectroscopy, people exploit the fact that you have these very narrow frequencies that you can relate to an RF frequency by means of the repetition frequency. But what we do is that we don't use the whole pulse train of the frequency comb, but we just take 2 pulses for a Ramsey type measurement, as I'll explain further. And so what we exploit is the fact that we can change the timing between the 2 frequency comb pulses very precisely on the level of hundreds of attoseconds. And it's also very important, like I said, that we can know what the phase slip from pulse to pulse is. So the method that we use is called Ramsey-comb spectroscopy, and this was developed in our lab over the past several years. And it works as follows. If you consider a 2-level system, and then we send 1 resonant frequency comb pulse onto our atom or molecule, that then sets it into a superposition of ground and excited state. And that superposition, which is depicted here on top, is going to precess at the transition frequency. And then sometime later, and this time is determined by an integer delta n, multiple of the repetition period of our frequency comb. Sometime later, we send another resonant pulse in, and that also excites a superposition that also precesses at the transition frequency. And so these 2 superpositions have a relative phase between them. And in this particular example, you can see that they're slightly out of phase and we get destructive interference. And now you can tune the relative phase between them. So the relative phase between them is determined by the time between the 2 pulses, but also by the phase slip from pulse to pulse. And we can tune the relative phase by moving the pulses further apart. So we see here that I move the second pulse a little further away, and now the 2 contributions can constructively interfere. So that's the principle with which we can make 1 Ramsey fringe by continuously moving, well, not continuously in steps, but continually moving the second pulse a little further away and probing the phase evolution of our atom or molecule. And in this way, we get a signal that is a sinusoid that oscillates at the transition frequency. So the argument we see is it's the delta t is the time delay between our 2 pulses, times the transition frequency, plus some phase shift that in an ideal world would be exclusively the phase shift from frequency comb pulse to frequency comb pulse, which we know very well. Now, the power of Ramsey-comb spectroscopy is not in doing 1 of these fringes, but actually many of them. But because we have a frequency comb, we can not only take 2 frequency comb pulses to do this, but we can use multiple pairs, as I'll now show. So we can take 2, say, adjacent ones, and the repetition time of our laser, of our frequency comb, is 8 nanoseconds. So delta n is the index for the pulse after the first pulse. So if we take delta n equals to 1, so 8 nanoseconds, that's the time delay for the first pulse that you would have here. And then we change the repetition frequency of our laser and probe the phase evolution of our molecules or atoms. Then we can choose a different pair of pulses. Go further apart, delta n equals to 2, so 2 times 8, 16 nanoseconds. So we have free evolution time of 16 nanoseconds for the first point along this fringe. And then again, we change the repetition frequency to probe on the order of hundreds of attoseconds the phase evolution. And we can keep going and go, say, all the way to n equals to 45, 40 nanoseconds, and do the same thing. And now what this gives us is that we effectively probe a very long free evolution time. And when we fit the frequency that we want to extract, we have a very long lever arm. So we have a very sensitive fit. Now, that's not the whole truth. So here I show some fringes that we measured in H2 of the X3F transition at delta n equals to 3, 15, 27, and 39. And the way that we actually extract the transition frequency is by fitting each of these fringes with a reference frequency, but with a variable phase. So they have a variable phase, and we can then assign a relative phase between each of these fringes compared to a reference phase. And then we can look at the phase evolution as a function of time and minimize that as a function of frequency to extract the transition frequency. And I can talk about that later if somebody has questions. But the important thing is that by doing this, all delay independent systematic shifts drop out. So notably the AC Stark shift, which is actually very strong for any one of our pulses, as long as we can keep the energy of our pulses the same, will drop out because it amounts just to a constant phase shift on all of our fringes. However, delay-dependent phase shifts will cause a frequency shift. And so we're going to have to be very careful that we don't have any of those, and I'll discuss that as we go along. And finally, for the actual acquisition of data, we do what we call random scanning. So instead of acquiring a full fringe at a given interpulse delay I mean delta n equals to 3, and remember that this means 3 times the 8 nanosecond period of our frequency comb. We acquire them in a random fashion, changing the repetition frequency as is shown here, and then we reconstruct the fringes afterwards. And in this way, we can reduce transient effects from our laser system. So that's the method that we use, but how do we actually do it experimentally? Well, we need 2 frequency comb pulses that can be amplified enough to allow for nonlinear upconversion to the desired wavelength. So in the case of the H2 experiment, it's around 202 nanometers. In the case, say, of our helium plus experiment that Akira mentioned on Monday, we need to have enough energy here to generate high harmonics. And so the way that we do that is by having a frequency comb, which we synchronize to a double pulse pump laser. And the double pulse pump laser will emit 2 pump pulses that are separated in time by precisely the free evolution time we want for our Ramsey measurement. And these pulses are about 20 millijoules per pulse. And so we send the pump pulses into an optical parametric amplifier together with the full pulse train from the frequency comb. And in this way, only those pulses from the frequency comb that are overlapped in space and time in the, we call this OPA, in the OPA are amplified. And in that way, we can go from about 1.2 picojoules per pulse to around 2.8 millijoules per pulse. And the reason that we have such low energy in the pulses before the OPA is that we have to clip the spectrum of our frequency comb pulses to make sure that we don't excite any neighboring transitions. So we actually cut the bandwidth to about 0.2 nanometers. And another important aspect of the OPA is that in contrast to amplifiers based on optical pumping, it doesn't have a memory effect. So the amplification of the first pulse should not affect the amplification of the second pulse. However, the OPA process is known to have the possibility of inducing phase shifts on the amplified frequency comb pulses, notably if you have any sort of intensity jitter from your pump pulses. And so this is something that we're going to have to measure and monitor to make sure that we don't get a frequency shift, as I mentioned earlier. And for that, we have a dedicated phase measurement setup. So this is a setup to determine the amplifier phase shift. And I'll show in the following slide how it works. But from this slide, you just have to keep in mind that the frequency comb pulses are split with a beam splitter, and we have an unamplified, so the beam splitter is before the OPA, we have an unamplified reference frequency comb pulse, and then the other half of the light goes through the OPA, and we have an amplified pulse. So here's the phase measurement setup, and what we do is, you see here we have a little pulse, that's the reference pulse, and the big pulse, that's the amplified pulse. That's the pulse that got amplified in the OPA and which may have some sort of phase shift relative to the unamplified pulse. Now we have 2 of those pairs. So here's one pair, here's the other pair, which are again separated precisely by the time that we want for our Ramsey measurement. And what we want to do is to extract some interference pattern from this pair on the right, say, and from that interference pattern, extract some phase. And we do the same thing for the other pulse pair. We extract another phase, and we look at the difference between those 2 phases. And we need to see if that difference changes as we move the pulses further apart. So that's what this setup is for. So we send them both through a fiber to ensure perfect mode overlap. Then we clean out all the other frequency comb pulses that we don't want to look at using 2 Poeckel cells. We use a third Poeckel cell to vertically displace one of the 2 pulse pairs. So let's say we displace the first one so that we can look at the interference pattern of both pulse pairs at the same time. So after vertically displacing them, we send them onto a grating and then look at them on our camera. And so for each pulse pair, say the one on the right here, we get an interferogram, which is here on the top. And let's say that the second pulse is on the bottom. And from this interferogram, like I said, we extract a phase, and also from the one on the bottom, and we compare. And we then compare them as a function of delay. And that's what I show here. So this is actual data massaged to be PowerPoint friendly so that I could show you what I want to show you. So like I said, we measure the interferogram, we get a phase, and then we plot it as a function of delay. We do it again. We have now for a different pulse pair from our frequency comb, a different interferogram. We extract a phase from the top, from the bottom, get a relative phase, and we plot it. And then at delta n is equals to 45, we do the same thing. And these are the delays that we use for the Ramsey-comb spectroscopy measurement. We then do a linear fit through these points and determine a slope. And from this slope, we can extract a frequency shift that we then use to correct our measurements. And we do this at the beginning of the day before any spectroscopy, and at the end of the day, we average over all the slopes, and then we correct for every day's measurements using this equation. So here's the rest of the setup we saw already up to here with the amplified frequency comb pulses. We then send them through 3 BBO crystals, where by means of second harmonic generation and some frequency generation, we can go to 202 nanometer light. And we split the light, the DUV light, into 2 counterpropagating arms that will interact with our atomic beam at 90 degrees. And on either side, we have a λ/4 wave plate that turns the linear polarization into circular polarization to reduce the probability of exciting the molecules with 2 photons from the same side. Now we have the molecules coming from a liquid nitrogen cooled pulsed solenoid valve that was developed in the group of Professor Merck in Zurich. And then the molecules fly roughly 1 meter to the interaction zone. And finally, we have a Sagnac interferometer to monitor how well our counterpropagating beams are aligned. So 6 nanoseconds after the second Ramsey-comb pulse comes in, we send an ionization pulse at 355 nanometers. And this pulse is going to ionize the excited molecules. And 6 nanoseconds after to ensure that its electric field doesn't affect the transition frequency that we're extracting. So that's the setup. And I mentioned previously that we were limited by the laser line width, the Doppler broadening, and the transit time broadening. And that's why my colleague Charlene put a lot of effort into improving the setup and addressing all of these issues. Notably, we changed our home-built titanium sapphire frequency comb laser for an ultra-stable laser frequency comb from Menlo Systems, which has 1,000 times narrower line width and allows us to have a locking of the repetition frequency, which is much more stringent. So we have a much reduced timing jitter of our frequency comb pulses. So if you imagine that we do the Ramsey-comb with these 2 pulses, then if they're jittering about, it's going to wash out the contrast of our fringes and give us a larger uncertainty in the fit. Then this is the vacuum setup that we have now, but we didn't have this before. So thanks to the new solenoid valve from Zurich, we have a higher molecular beam density. We also have, I should mention, a longer vacuum chamber that allows for better collimation. So we have a higher molecular beam density, which means that we have stronger signal. And that also means that we can afford to lose some of that signal in order to slow down our molecules further. So we mix our H2 molecules with neon, or our D2 molecules with neon. And through collisions, because neon is much heavier, we can slow them down by about a factor of 2. So this allows us to have slower molecules and reduce the Doppler and transit time broadening. And it allows us to have 2 different temperatures to work at for a Doppler-free extrapolation. So we have pure H2 or D2, and then we have the twice as slow mixture with neon. And they're both going to be liquid nitrogen cooled to about 100 degrees Kelvin. One more thing that Charlene worked very hard on was to increase the stability of the pump pulses, because that directly translates into stability of the amplified frequency comb pulses. And finally, the phase measurement was upgraded with an image intensifier that has a 4 nanosecond gate time, so we can cut out the background much better. So here's a typical first order Doppler free extrapolation of our X2EF measurement in H2. Whereas I said we have two velocities. One is pure H2 and one is in a mixture with neon. Pure has around 1300 meters per second and the neon mixture is around 700 meters per second. So we measure the transition frequency at both temperatures and then extrapolate to zero velocity. Here is the Doppler free extrapolation for the whole measurement campaign in H2, where in black we see the mean and in solid pink we see the standard error. And I mentioned that we're insensitive to the AC Stark shift, but that's only if we can perfectly feedback on the energy of our pulses. And because nothing is perfect, we can't exactly do that. So we nevertheless have to measure and see if we have some residual AC Stark shift. So we measure at two different energies, the transition frequency. Again, extrapolate to zero energy, get a slope, and evaluate that slope at the energy at which we do our measurements. And so here is, again, the plot for the whole measurement campaign in H2 for the AC Stark shift, where we can see that it's not exactly zero, but it's quite close. The mean is quite close to zero. So we get a shift of 27 kilohertz with an uncertainty of 23 kilohertz. So this brings me, and I think I'm roughly on time, to the error budget for H2. So we have the transition frequency, which is corrected for the first and second order Doppler effect, and any sort of amplifier phase shifts with an uncertainty of 21 kilohertz. Then we have the AC Stark shift correction that I mentioned with 23 kilohertz uncertainty. One thing that I didn't mention is that we not only check for phase shifts due to the amplification in the OPA, but we also have to check whether the setup we use to determine phase shifts from the OPA itself induces any phase shifts. So that's what this phase measurement setup correction is. And we see that it induces a little bit. So we have a -8 kilohertz correction for that with an uncertainty of 1. Then we compensate for Earth magnetic fields in the interaction zone. So the Zeeman shift should be 0 for that reason and for the reason that we're in para H2 with 0 nuclear spin. But we nevertheless measure it and get an uncertainty of 1 kilohertz due to errors with the magnetometer that we use. And finally, we have a DC Stark shift correction, which again, because we have a homonuclear molecule with no permanent electric dipole moment, we expect to be 0, but we measure it to test for any, for example, quadratic Stark shifts. And we get a shift of 1 kilohertz with 1 kilohertz uncertainty. And finally, there's the clock to which we reference our frequency comb. So if we put it all together, we get the transition with 31 kilohertz uncertainty. And now if we do the same thing for D2, because D2 is roughly twice as heavy as H2, we could probe a much longer free evolution time. And so many of these effects are reduced. So you can see that, for example, the uncertainty from first and second order Doppler combined with amplifier phase shift is only 13 kilohertz here. And so we keep going down the list, do the same thing, and have 19 kilohertz uncertainty on the D2 X2EF transition. And I should stress that this is all preliminary. And that then brings me to the conclusion. So we measured the X2EF transition, Q0 transition in H2 and D2. In H2 with 31 kilohertz uncertainty, which is about 1 times 10 to the minus 11 uncertainty, relative uncertainty. In D2 with 6 times 10 to the minus 12 relative uncertainty. And as an outlook, one could combine, as we've heard already before, these results with the recent work that Joanna will talk about at 5 from Zurich of measurements of high-end Rydberg Stark states of H2 for a more precise determination of the ionization of H2 and therefore a more precise determination of the dissociation energy. And finally, we are also intending to measure HD, and we already saw a very strong first signal. And our lab is also very busy. I didn't talk about this, but Akira mentioned it. Very busy also trying to measure the 1s to s transition in helium plus. So with that, I'd like to thank you for your attention, thank my group, and especially Charlene for help in preparing this talk.
Thanks, Andres. Any questions or comments? Frederick, the microphone.
So you want to be fast on the last slide. So the reason why D2 is so much better is simply because you are slower, or could you
Yes.
just
Basically, yeah. Because it's heavier, so
and
it's also
in
slower.
D2 you put also, you mix with neon,
As well, yeah.
and then you should have the same velocity as with H2.
No, it's even slower. So we have the pure D2 and the mixture of D2 with neon.
But the mixture with neon should be the same speed in H2 and D2 if neon is in surplus, or
I can't remember right now if it's exactly the same, but it's roughly, I think. You mean between the two mixtures, how fast is one relative to the H2?
I would have thought that if you put a lot more neon than H2 or D2, the velocity of the supersonic beam is determined by the neon component of the
I see
beam,
what you mean.
and the velocity should be similar.
Yeah. To be honest, right now I don't remember off the top of my head, but I can check afterwards and we can talk about it.
It's a supersonic extension, or it's a buffer gas?
No, it's a supersonic expansion. There's a question here.
Hello? I think it's on here. So why are you using neon as a gas and not xenon or something really heavy?
We also tried, for example, with argon, but found that it just didn't work as well. We got too little signal in those cases. Yeah.
I'm not sure if I understand this AC Stark shift correction. Are you saying that the AC Stark shift is the same for the two pulses, or are you saying that you have no AC Stark shift whatsoever? That means you can crank up your laser power to infinity and still have no AC Stark shift?
It's the same for the two pulses.
Okay,
or it
so
should
there is
be
an
the
AC
same.
Stark shift,
Yes.
but it's just the same.
Yes, there's a very strong AC Stark shift.
Got it.
Or we do our best to keep it the same. You want to, yeah?
Oh.
So how does a lambda/4 wave plane prevent that two photons from one pulsar are absorbed together?
Yeah, I was afraid of this question. So, yeah, at the moment, I can't remember. It's the combination of having the circular polarization and tripped pulses. But I believe it was the group of Professor Udom who wrote the paper where they described this effect. No?
I think it's just the selection rule, the two photon excitation. I mean, they're complicated, the selection rules. But if you have an S-to-S transition, you can see that from 0 to 0, you can see that only two counterpropagating photons can be absorbed. Otherwise, angular momentum will not be conserved. And then you don't have the Doppler. I'm not sure if that is answering your question.